Hello, I am Pradeep Kumar, Professor. Welcome you to the lecture on Fluid Statics as Module 3. It is being presented in 6 parts as listed. Similar to earlier lectures, in this lecture also, presentation is in conversational mode and with a stress on the concepts and practical applications. We know diagrams speak clearly about a subject than tons of description of the subject. Same is the case with the determination of total pressure and the center of pressure pertaining to plane surfaces. As discussed in the earlier lectures, a plane surface submerged in a static liquid will experience hydrostatic pressure, the variation of which follows hydrostatic law, that is P is equal to gamma h, where h is the depth of liquid on the surface, gamma is the specific weight of the fluid. And we also know a plane surface can be oriented either horizontal, vertical or inclined. For example, if the surface is held horizontal, then the depth of fluid on the surface is same everywhere. Hence, pressure is also same everywhere. This amount of description can be very simply represented diagrammatically as shown in second figure. It represents pressure diagram pertaining to a plane surface held horizontal in a liquid. The pressure diagram resembles a rectangular parallelepiped. So, from the above discussion, we can infer a pressure diagram is a pictorial representation of pressure distribution on a surface. A pressure diagram is developed by plotting pressure values to some convenient scale. For example, pressure at a point be 25 newtons per square meter. You may opt 10 newtons per square meter as 1 centimeter. So 25 newtons per square meter become a line of length 2.5 centimeters. This convenient scale depends upon space available on the drawing sheet or answer sheet and the details you want to represent through the diagram. As hydrostatic pressure is normal to the surface, the pressure lines are normal to the surface. Now, consider a plane surface of width W units and height D units immersed vertically in a liquid. Let the top and bottom edges of the plane surface be at a depth of h1 and h2 from the free surface. Consider a point on the top edge, so the pressure at that point is gamma h1. The pressure at the bottom point is gamma h2. Then the pressure at every point on the top edge is P1 is equal to gamma h1. The pressure at every point at the bottom edge is gamma h2. I am sure in your mind you must be entertaining a doubt. Instead of describing so much, the presenter could have drawn a simple figure. That's exactly the role of the pressure diagram. Now, let us develop pressure diagram corresponding to the above description. A glance at the figure indicates the distances of top edge and bottom edge are h1 and h2 respectively, and the pressures at top and bottom edges are gamma h1 and gamma h2 respectively. Now, pressure distribution along the vertical line passing through top edge and bottom edges as shown. Let us consider complete surface. Observe from the figure, the pressure distribution diagram resembles a trapezoidal prism. Area of the plane surface is W by D. Average pressure on any vertical line is gamma into h1 plus h2 by 2. The volume of the prism gives you total hydrostatic force on the plane surface, that is area into average pressure value as shown in figure. So capital P is equal to total hydrostatic force is equal to W by D into gamma into H1 plus H2 by 2. Coming over to the location of center of pressure, it is located at the centroid of the trapezoidal prism representing the pressure distribution on the surface. So its distance from free surface h bar is the sum of the distance of the top edge from the free surface plus distance of centroid of the prism from the top edge of the surface. It is given by h bar is equal to h1 plus 2 into gamma h2 plus gamma h1 by gamma h2 plus gamma h1 into d by 3. From the known values of h1, h2 and gamma and D, the position of center of pressure from free surface can be determined. The next case is pressure diagram pertaining to pressure distribution on an inclined plane surface submerged in a liquid. In this case also, the depth of the liquid varies from point to point. Hence, pressure also varies from point to point. So, the pressure diagram can be represented as follows. Now, let us discuss multiple choice questions. Pressure variation with depth is linear. Say yes or no. Yes. Area of the pressure diagram gives pressure force on the plane surface. Say yes or no. No, because it is the volume of the prism that gives the force, not the area of the pressure diagram. Slope of the pressure variation line changes in the case of a plane surface supporting multi-density fluids. Yes or no? Yes, because pressure variation is influenced by variation in density of the fluid. Pressure lines are normal to the surface. Yes or no? Yes, let us work out a problem. Draw pressure diagram for a plane surface of size 2.5 meters by 5 meters immersed vertically in a static fluid as shown in figure. So the problem is on pressure diagram, size of the plane surface and position of the plane surface with respect to free surface. Specific gravity values of the two fluids and their depth are given. Continuum is valid, plate is at rest, fluids are immiscible and static. Specific weight of water, that is gamma of water, is 1000 kg force per cubic meter. The thing to be determined: pressure diagram, total hydrostatic force and position of center of pressure. Now let us name the salient point. Let Fs be the free surface, A be the top edge of the plane surface, B be the junction point of the two fluids, C the bottom edge of the plane surface. Now depth of the top edge of the plane surface A from the free surface, that is HA, is 2 meters. Specific gravity of the top fluid G1 is 0.8. Therefore, its specific weight is equal to gamma 1 is equal to 800 kg force per cubic meter. We know specific gravity and specific weight of fluid are related through specific weight of water. Therefore, pressure at A is equal to gamma 1 into HA, 1600 kg force per square meter. Now, let us find out the pressure at B. The depth of interface of the two liquids B from free surface is HB is equal to 7 minus 2, 5 meters. Therefore, pressure at B is equal to gamma 1 into HB, 4000 kg force per square meter. Therefore, the pressure at B is 4000 kg force per square meter. Now, pressure at C. We know it is the sum of pressure at B and the additional pressure due to the lower fluid up to C. Specific gravity of the lower fluid, that is G2, is equal to 1.2 as given in the problem. Its specific weight gamma 2 is equal to 1200 kg force per cubic meter. Depth of the lower fluid from the interface to the bottom point is HBC is equal to 2 meters. Therefore, pressure at C only due to this lower fluid 1200 into 2, 2400 kg force per square meter. However, the pressure up to B is 4000 kg force per square meter. Therefore, total pressure at C from free surface comes to 6400 kg force per square meter. Now, once we have determined the pressures at free surface at A, B and C, let us proceed with the development of pressure diagram. Choosing a suitable scale, pressures at free surface A, B and C are converted into linear parameters and the corresponding pressure diagram is drawn as shown in figure. Before concluding this lecture, let us recapitulate whatever that has been discussed. Pressure diagram, method of its construction and various applications. We also solved a problem along with a discussion on interview oriented questions. Before signing off, I request you to leave your comments in the comment section to enhance communication between us. Like and share the video among your friends and concerned. Subscribe to my channel by clicking the bell icon. The best way of getting updated with the information on the latest videos pertaining to the other topics of fluid mechanics, hydraulics and hydrology in addition to career planning. Thank you very much and wish you an excellent future.